Hi, I am Nicholas Andrews, and we are the ASU District Solar Cup team. It's myself, Asaka Balima, James Foreman, Pat Wansing, and Annie Schutzinger. And we had a mentor on our project, Raja Ayanar, who is a faculty member at Arizona State. So this is our team, who I just described just a second ago, pictures of us, and our development plan. I will hand it over to James.
Okay, so one of the challenges we faced as a team was determining how to achieve buy-in from the community. We put an emphasis on the estimated $2 million of inventory that could be saved if a blackout were to happen. Our PV and battery storage solution could provide the required power to ensure the inventory was safe. This was not enough. We also wanted to implement UNL's master plan and principles into our design. We looked into the university's principles and found that the buildings must relate to and define an outdoor campus. This would become a challenge as the solar panels are dark and contrast with many of the existing buildings on campus. The large BESS containers location would also be a problem. To remedy these, we placed the majority of the solar panels out of sight on rooftops and selected a location for the BESS container that would be hidden by existing trees. These small changes would ensure that UNL's campus remains beautiful without any distractions. Next slide. So here's just like an overview of the timeline. So for the first 2 months, it'll be appropriation and engineering design starting July 1st. The next 3.5 months would be the procurement of the materials and equipment. And then construction will start January 15th, go for 9 months and end on December 15th, 2022. And then we'll have an in-service date of December 20th, 2022. Next slide.
All right, so for the conceptual design, we decided we want to place the panels by identifying different location options and comparing them against relevant specifications. So for this analysis, we decided to limit the PV arrays to building roofs. As you can see on the left side, checks most of our boxes. And then the building roofs are flat, they receive minimal shading. Most of the areas do not have a lot of trees or other buildings nearby and didn't require significant mounting costs, and they don't conflict with UNL's master plan intent to maintain green space, while we chose the ground mounts, which has the community engagement and other aspects for the ground mounting system as opposed to a carport or other locations on the building. We continue the conceptual design with the equipment selection process. So it involves selecting the make and model of the main components of our PV system, and which are the panels, the inverters, and mounting hardware. The selections were made using the specifications of production, durability, manufacturer quality, and ease of installation. The below slides provide the example of how the selection was made for the panels from a compilation of different makes and models in the modeling software database for SAM. So a similar system was followed for the inverter and the ground mount panels, which you can see on the right-hand side. We chose the Chint inverter and the elevated panel claw. There we go. To design the rooftop panels and the agricultural PV site, we used AURORA for modeling. And the first step was to model the physical infrastructure using the photographs and stuff from Google Earth and things like that to do the layout and stuff of the rooftop design. So also the optimal model orientation, tilt, and interrow spacing was identified through research and iterative modeling inside AURORA Solar. And with the final layout, production profiles were generated using weather and irradiance data with the on-site PV generation of each building shown here on the bottom right. The maximum rooftop production we achieved on an average energy offset of about 15% of the annual building load. And you can see from the graph on the far right about, the shaving from the load. The maximum rooftop production we achieved an average energy offset of 21% on the city campus and about 17% in the East campus. And I think our overall panel count was about like 8,300, I think, if you add everything together. And the graph on the far right, you can see how the offset helps peak shave the load when there is the sun out during the daytime, and then when the peak load happens during the daytime for the energy usage. So here we go. Our distribution system impact analysis proved that our PV system can be safely integrated within the distribution network. In this study, we focused on several aspects of AC power parameters, like voltage magnitude, real and reactive power. The competition provided the base circuit and open DSS that you can see, which we added the temperature and irradiance data and placed the system elements of our conceptual design, and then ran the modified circuit graph, voltage and power flow to check the transformer loading, verified voltage levels, and they were all within the verified limits, and no elements required upgrades. All right, battery integration. So there are several methods of generating revenue through batteries. We can do value stacking of the building load shape, peak shaving, and load shifting and resiliency. And for the peak shaving, you can see there, it reduces the demand charges as the peak is moved, obviously, for load shifting, and reduces the time of energy use charges and resiliency, which adds value by providing backup power during our power outage. We use REOP system advisor model to test and build the resilience method into our financial model. And the size of the battery includes the energy capacity and the power rating. And we were interested in identifying the optimal combination of the parameters. There we go. Using the computer program REOP to Light, we conducted an energy resilience optimization analysis to determine a reasonable battery size for our building in kilowatt and kilowatt hours, and also provide the most cost-effective battery integration. Additional input parameters were the utility electric rate, the hourly load profile, and outage duration that we were trying to model for. And we found a reasonable power and energy range shown on the slide here. And we were, I'm sorry about that. So for the financial analysis, I'll hand it back over to James.
Thank you, Nick. Next slide. As the primary developer of this project, we wanted to ensure that we achieved the financial goals of UNL, including achieving an internal rate of return in the range of 7 to 14% at a net present value of $0. To meet this goal, we strive to have an optimized PPA rate, which could secure our desired IRR range and at the same time maximize customer savings. These goals were challenged by low electric rates, much lower than the national average, and the SDC rule of no solar exports. We remediated these challenges with the dollar per DC watt cost reduction and peak demand management. Next slide. We revisited our approach to determine the economic model parameters, mainly the DC per watt cost for construction and installation. Using the versatile skill set available in our team, we took the realistic approach to estimate this project and estimated the DC per watt cost using top-down estimating technique. The estimated costs were not too far off from the nationally benchmarked costs and were based on weighted PV production for any given type of system, whether that be ground-mounted or roof-mounted systems. Next slide. Cost reduction was made possible by using every opportunity to implement value engineering and economies of scale. We ensured that no governmental incentives should go unused. As an example, availing sales tax exemption. The labor man hour rate used in estimation is based on prevailing wages and fringe rates in Lincoln, Nebraska. Next slide, please. Finally, we reiterated the financial inputs, the construction and hardware cost, the utility charge that is based on Lincoln Electric System, the local utility in Lincoln, Nebraska. Next slide, please. PV installed capacity for city campus is 945 kilowatts, and the capacity for East Campus is 2.248 megawatts, which includes ground-mounted agrivoltaic system for the agriculture site and a rooftop PVs for the buildings. The added agrivoltaic PV system at the agriculture site was designed to have the capacity that was large enough to offset the load consumption for a cluster of 14 buildings. Next slide. The economic modeling was done for each building with a recommended PPA range capable of generating an IRR between 8 to 10%, which is between 8 to 10 cents per kilowatt hour. Next slide. The financial analysis of the animal science complex was done using SAM and REAP Lite. A recommended PPA price in the 10-cent range was utilized and was capable of generating an IRR between 8 to 10%. Next slide. Next slide again. Before concluding, I would like to highlight all of the achievements our team has accomplished over the past few months. As a team, we have achieved UNL's sustainability goals for the campus in a financially viable way that reduces carbon emissions and inspires and informs the community surrounding the campus. To conclude, these past 2 semesters have challenged each and every one of us and forced us to grow as individuals as well as a team. From the demanding deadlines to the juggling of classes, work, social lives, and living through a pandemic, our team has overcome each challenge we have faced. It wasn't easy, as many of us had conflicting schedules and opinions and were often stretched thin. To combat this, we identified our strengths as a team and made each decision as a team. This ensured that we were able to provide the best possible presentations and deliverables that we could offer. I would like to thank our team for all of the hard work and dedication they have put into this project over the past 2 semesters. Thank you guys for your time.